Hi, in this video we are going to show that a band-limited signal cannot be time-limited. Okay, what do we mean by a band-limited signal? Remember that x of t is a band-limited signal Okay, here we are going to assume that in order to avoid the trivial case, we are going to assume that the band-limited signal is not the zero signal. It is not the zero signal. Zero signal means the signal which takes the value 0 for all t, from minus infinity to plus infinity. It is not the zero signal. So it is an arbitrary band-limited signal, but to avoid the trivial case, it is not the zero signal. That is, remember the definition of the band-limited signal. The Fourier transform of x of t, x of omega, is 0 for absolute value of omega greater than omega m. There is a certain constant omega m such that for all omega greater than omega m or less than minus omega m, the Fourier transform vanishes. Okay, now we know that if we sample the signal with a sampling frequency omega s greater than 2 omega m, we can retrieve the signal exactly from its samples. Now, suppose that we sample x of t with a sampling period capital Ts, and obtain the samples. X of m Ts. Okay, m is 0, plus minus 1, plus minus 2, etc. Okay, so these are the samples of x of t, and in order to avoid aliasing, omega s, which is equal to 2 pi over capital Ts, is chosen to be greater than 2 omega m. Okay. Now, we know that x of t can be retrieved from its samples by using the Shannon sampling theorem, and in fact, equivalent to the Shannon sampling theorem, we have obtained the Shannon interpolation formula. So x of t can be retrieved from its samples by using Shannon interpolation formula, which is the following expression: x of t is equal to m from minus infinity to plus infinity, x of m ts, the samples, multiplied by sinc t over ts minus m. Okay. Now, this formula has been obtained in the video related to the Shannon interpolation formula. In fact, let us remember very quickly the idea behind Shannon interpolation formula. Remember that the sampled signal xs of t is in fact the signal model we use in terms of sampling of x of t by the impulse train, which is the periodic repetition of unit impulses with period ts, and the Fourier transform of xs of t is in fact composed of shifted replicas of the Fourier transform of x of t. These replicas are again repeating themselves with period omega s, okay, in frequency domain. And in order to retrieve x of omega, we want to get rid of all the shifted replicas except the portion of the Fourier transform centered around zero frequency. And in order to do that, we use an ideal low-pass filter to obtain x of t back from xs of t. In fact, this sinc function is obtained as the inverse Fourier transform of the frequency response of the ideal low-pass filter. Since the ideal low-pass filter is a rect type function, its inverse Fourier transform is sinc in time domain, the sinc function in time domain. Okay, but all the details of the computation of the Shannon interpolation formula is in the video related to this topic. Okay, so x of t is obtained by means of this formula, the Shannon interpolation formula. Okay. Now, if you look at the formula, we have, okay, in this formula, consider the term sinc t over ts minus m. Okay. Now this term can be written as sine of pi t over ts minus m pi divided by pi t over ts minus m pi. Okay, so we have this expression. So the sine function can be written as, by using a trigonometric identity, sine pi t over ts cosine m pi minus cosine pi t over ts sine m pi. Okay, divided by this pi t over ts minus m pi. Now sine m pi is equal to 0. Okay, this term here is 0. And cosine m pi is equal to minus 1 to the power m. Okay. Therefore, x of t can be written as m from minus infinity to plus infinity. Okay, in fact, this term sine pi t over ts does not depend on m, therefore it can be taken outside the series expression. So we have sine pi t over ts, okay, and then we have m from minus infinity to plus infinity, minus 1 to the power m divided by the term pi t over ts minus m pi. Okay. Multiplied by, of course, x of m ts. Okay, so we have this version of the Shannon interpolation formula. Okay. Now, we ask the following question. Is it possible that this band-limited signal, which is not the zero signal, which is not identically equal to 0, can it be a time-limited signal? So, can x of t be a time-limited signal? Now we are going to see that the answer to this question is negative. It is not possible that a band-limited signal is also time-limited. Now how can we show this? We are going to prove this by assuming that the signal is time-limited, and we are going to obtain a contradiction. Okay, suppose that x of t is time-limited. That is, there exists a capital M, which is a positive integer, such that x of t is 0 for absolute value of t greater than MTS. Okay. So x of t now becomes not an infinite series expression, but it becomes a finite sum. So x of t becomes by using the expression we have just obtained, sine pi t over capital Ts, and now m is running from minus capital M to capital M. X of m Ts minus 1 to the power m divided by pi t over Ts minus m pi. Now, if we look at this expression carefully, in the numerator we have powers of minus 1. So it is either minus 1 or plus 1. In the denominator we have a constant multiplied by t minus another constant, which depends on m. Okay, and m is running from minus m, minus capital M to capital M. So it is clear that if we rearrange these terms, what do we obtain? We obtain a rational function of t. That means it's a function which is expressed as a polynomial divided by another polynomial. So x of t is in the following form. It is sine pi t over Ts P of s divided by Q of s, where P and Q are polynomials. These are polynomial functions. Sorry, not s, of course. What is s? It is t. P of t divided by Q of t. Okay. So we have polynomials of t. Now, therefore, this is the expression of x of t for all t. But we know that for t greater than MTS, capital MTS, and t less than minus capital MTS, x of t is 0. So this implies that p of t is 0 for x of t is 0 for magnitude t greater than Ts, which means, not Ts, M, capital MTS. And this implies that P of t is 0 for, again, t greater than magnitude t, or absolute value of t greater than capital MTS. Now, we know that a polynomial is 0 only at its zeros, which are finite in number. But here we see that P of t vanishes over the continuum. You see that, for example, the interval t greater than capital MTS is the interval from MTS to infinity. So the polynomial is 0 over that interval. Now, if a polynomial is 0 over an interval, it can be an arbitrarily short interval, the polynomial must be identically equal to 0. Because, I'm repeating once more, a polynomial is 0 only at a finite number of points, which are called the zeros of the polynomial by definition. Okay? So other than the zeros, the polynomial takes non-zero values. If the polynomial is 0 over an interval, which means a continuum of points, infinitely many points, therefore the polynomial itself is identically equal to 0. So this implies that P is the zero polynomial. And therefore x of t is 0 for all t, which is again a contradiction. To what? To our original assumption that x of t is not the zero signal. We want to avoid that trivial case. Okay? So, this is the proof that a band-limited signal cannot be time-limited. Okay? Thanks for watching.